really gives you the secret behind universality. The idea that you have only a few relevant operators in these big multi-dimensional spaces of all the coupling parameters in your Hamiltonian. And in particular, all these microscopic details that go into the sort of the Hamiltonian at scale level 1, or at the UV, they make up, most of them make up this huge space of irrelevant operators. So if you're at a fixed point and you perturb in some operator corresponding to an irrelevant operator, like you just turn around and flow right back into the fixed point. Right, so it's like a set of K star, right? You have all these RG flow directions. And if you perturb away from that fixed point, you just flow back into it. So they don't affect the long wavelength physics. So what you're doing on the assignment is an Ising model in a field. You'll see two relevant variables there that have to be basically adjusted to get to the critical point. So T and H. So many of the other, say, higher order couplings, T is relevant, H is relevant. If you had couplings proportional to, say, the order parameter cubed or order parameter fifth, these will turn out to give you irrelevant operators. Right, H couples to the field linearly. You could have a cubic coupling and so on. But these won't give you relevant operators. They won't give you scaling dimensions that are relevant. The same is true for even couplings higher than a certain order. We'll explore that a bit more. Basically, we're going to start doing a 5-4 sort of continuum analysis of the RG. And you'll see that anything higher than couplings to the fourth order, 5-4, M4, whatever you want to call it, result in irrelevant couplings. You're arguing for irrelevancy of what? Something on your assignment. Oh, the lattice unit, the lattice constant. Let's talk about that a bit today. Last time we formalized the scaling hypothesis. It's very simply the idea that you have a scale factor and then you rescale and renormalize. So after one RG step, which is what the prime means, you take length scales and you reduce them by a factor of B. That includes the correlation length. What else? The number of degrees of freedom, n prime, is reduced also. Depends on dimension. All right. And The important one is the free energy, just B to the D, or if you will, the singular part of the free energy density. And you know, B is whatever. B was 3 in the example I did in class, in real space. You know, you're picturing B as defining the blocks. You're looking at B equals 2 on your assignment question 5. So the way that variables, if you will, transform under one step of the renormalization gives you the scaling dimension. It's defined by A prime B to the x A, whatever A is. And importantly, last class we derived a scaling dimension for the physical Ising variable. What is it? B to the D minus YH sigma. We're going to talk about more about what this means. You can also imagine this rescaling the field. If this is the field in real space, which is just sort of a generalization of the spin variable, has the same scaling dimension. We're going to need the scaling dimension of the field in momentum space soon. So we'll have to Fourier transform this relationship. And in particular, this led to the scaling dimension for the 2-point correlation function, which we derived last time. It's basically just, you know, it's the product of two fields. So the scaling dimension is just a factor of 2. So it's 2D minus 2 YH GIJ. And to derive the scaling functions, which give us the exponents, we just basically invert this. So if I write, you know, IJ separated by a distance r, then my 2-point function, which depends on r, depends on the reduced temperature, and I've set h equal to 0. I wrote last time like this. I'll just invert this. So it's minus 2d plus 2yh. So this is like g prime here. So r prime, I know from that relationship. So it's simply like this. And then I have a t. I've been writing these in terms of the scaling variable u of t, which is just generalized. I've made an assumption on these. So t is a scaling dimension. That's basically what defines y of t. And remember, u of t, I'm somehow assuming, is proportional to just the reduced temperature. Although generally you need to, you know, diagonalize that matrix. You have to solve that eigenequation in order to see exactly what these variables are. Okay, so this is all stuff from last time we talked. I looked at the form of this function away from t equals tc, and I argued that, you know, the argument of this relates to the argument of the exponential, which actually defines the correlation length. But this is more powerful precisely at tc. Where my small t is equal to 0. So everything just depends on r. And sort of the divergence is governed by this. There's no length scale in the system at all, besides, in this case, the distance separating I and j. So I just identify that length scale with a rescaling factor. Then I would see, if I just set those two things to be equal, then this actually would govern the divergence as a function of r. Then g would go as r to the minus 2d plus 2yh. And this part, in principle, could be, by this logic, analytic. This isn't exactly right. But this tells you that I could have, some r dependence with an exponent in, precisely at the critical point that's governed by basically the scaling dimension here. So what is that exponent? This is a little bit trickier for the two-point function. Okay, the identification of this with, say alpha, beta, gamma, that type of thing. You're going to address this in your assignment. If you look at question 1, you're essentially looking at a dimensional analysis of Landau theory, in some sense. You're looking at the Gaussian approximation, you're Fourier transforming things. You see the dependence in part C of question 1. R to the minus d plus 2, and I've added another exponent in there called eta. So the tricky thing about the two-point function is there's eta, which is called an anomalous dimension. And that, it's anomalous because it doesn't occur in that dimensional analysis that you're doing of essentially Landau theory. So everything I've said about relevant and irrelevant variables, I think is very self-consistent until you get to the two-point function, and then you have to worry about one irrelevant variable, if you will. So we're just going to go through that now. And the bottom line is there just exists an eta, and you can justify it in many different ways. Contained in Landau theory. Right, all of our exponents were in the Landau theory. If we looked at the, the values weren't correct, but the idea that the exponents, were there, at least came from Landau theory. If you look at this scaling dimension, if you will, and compare it to what you get in question 1 of your assignment, then you think, like I say, that scaling dimension is just minus d plus 2. But it's not exactly true. So assignment 3, you're going to look at the Landau theory. But that gives you, all right, what did I say, minus d plus 2, which would allow you to write yh in terms of d, essentially. but this isn't exactly correct. So in this case, an irrelevant field can affect this exponent. And I think anytime this occurs, then these are called anomalous. So this is the anomalous dimension. For most of the examples, I think everything we're going to calculate this eta would be 0. But it doesn't mean you shouldn't know that it's not there. So in particular, the irrelevant field is the lattice constant. And that's what you're looking at in question 4. You're just looking at the relevance or irrelevance of that lattice constant. But I've argued that this lattice constant doesn't matter. I've been arguing that, you know, the correlation length diverges. And so, you know, this long wavelength theory, because psi is very large, properly describes the system. But, you know, if you thought too much about it, you might say, well, just because when the correlation length diverges, if you're exactly at the critical point, there are no length scales. And so you could also make the argument that, you know, maybe fluctuations at all length scales matter, including length scales down to the lattice constant. And so the truth is that's just manifest in the 2-point function. These short distance, if you will, fluctuations that occur kind of at the UV. And if you took that into account, you'd have to redo the scaling. I'm not going to do it in detail, but imagine you have GR, everything else is 0, H, T, but I have to add an A in here. I would get something like and exactly at T equals TC, if I did the same thing and the distance that I consider between I and J, if I set that equal to my rescale length factor, this is not a rigorous proof, by the way. So then I would get G plus 2, G. So I would eliminate R in the scaling function at the cost of A over R. And that's supposed to be something very, very small. So I can imagine just scaling that thing away. But what you got to ask is, if I scale that thing to 0, does this just go to some analytic function or not? And in the case of the 2-point function, we can't assume that. That's basically the problem. I mean, it might be true. But the problem, it could be vanishing. Could be that there's an exponent governing how that thing vanishes. It could be that G1 A over R. Let's see, in the limit, A over R goes to 0, goes to, yeah, A over R to some exponent. And that exponent is the anomalous dimension. So then the full scaling function with a non-zero eta would be I'll just write it like this, R to the minus D plus 2 minus eta. So, I mean, there's no proof, like I'm saying, it's just, this is just actually what happens in the case of the two-point function. So you want life to be simple, but it's not simple. You know, the physical fact is that you get an anomalous dimension. And so the scaling, you know, is more complicated than what you see in Landau theory. And so that boxed equation at the top, minus 2d plus 2yh, actually turns out to be minus d plus 2 minus eta. So in this way, yh relates d and eta. And it's just the definition of the anomalous dimension. Again, it's 0 in Landau theory. It's 0 even in interacting fixed points. It's very close to 0 in many interacting fixed points. 3D02, you know, I think it's like 0.003 or something like that. It's very small. But the fact is that you can measure non-zero etas just by looking at scaling of the two-point function. Okay, so looks right. There's the anomalous dimension. And so together with the relationship between nu, which governs the divergence of the correlation length, so it's 1 over y, yt, those give another set of scaling relationships. We already saw what I was calling thermodynamic scaling relationships or something like that. These are called hyperscaling relations. I guess they're hyper because they have the dimension in them. There's 4 of them. And again, you just eliminate yt and yh from all these types of equations, you know, this one and this one. You have all the other equations for alpha, gamma, and so on. So hyperscaling relations have the dimension in them. So that's 1, 2. Here's one for gamma, nu. You can write these in different ways. 2 minus eta and delta. Which is the critical isotherm. Okay, so there's just relationships between all the exponents, come from the scaling hypothesis. And we could have written these down in a very simple way about, a class ago, except I wanted to be very careful about the anomalous, the existence of the anomalous dimension. And the other thing to note is that these things can be, in principle, violated. There's a dimensional dependence, and critical exponents, depend on dimension. So unlike the thermodynamic scaling relationships that I wrote maybe last class, you might find cases where these are violated. And I won't talk too much about the violations, but usually they correspond to some interesting physics. Okay, so that's the anomalous dimension. We're going to need the scale. What are we going to need? The scaling dimension of the field here soon. So remember, we derived that last time. I used it essentially to derive this. Just basically postulating the existence of eta. That gives us the hyperscaling relationships. Before I go on and use this scaling theory in order to perform a momentum shell RG, I just want to say one thing about finite size scaling. And so finite size scaling is important when we look at numerical simulations in particular. As I argued at some point, phase transitions, so and in particular critical points don't exist unless you're in the thermodynamic limit, right? So all these arguments rely on the fact that you have a well-defined thermodynamic limit, but there's no phase transition in principle, or to be precise, in any finite size system, like your numerical simulations. It doesn't mean they're not useful. I can actually argue for a way to extract critical exponents, say, or reduce temperatures from finite size systems by just constructing a scaling form like this. So I can do it for the free energy. I could do it for the 2-point function. But for the free energy, I could just imagine that I have another scaling variable that I have to worry about, which is the linear size of the system, say. So it's almost like putting in another variable like I did here, A. Let me forget about A. We're not going to talk about that length scale anymore. But I'm going to talk about the linear size of my L to the D finite size system. And L scales under one RG step as a length scale, just like R does up there. Okay, so this is the volume, that's the linear size. So then my singular part of my free energy density, which depends on all these relevant variables, can also depend on, I'll use 1 over L. Because in that case, when I go to the thermodynamic limit, then that no longer occurs in the free energy density. I know the scaling for my free energy. That's I invert that equation, so it's b to the minus d after one step. These are k primes. And then my L just picks up a factor of b, like that. So it's like a relevant scaling variable with scaling dimension y equals 1. Okay, I don't even have to write y. So I can consider n RG steps, like we always do. And that's a large number, but it's fixed. Okay, so and skip right ahead to calculating some physical observable that you get from an estimator in your, say, Monte Carlo or DMRG or ED or whatever it is. So susceptibility is an easy one. So calculate any physical observable. So let's do the susceptibility, which is the second derivative of the free energy. Okay, so the idea is we've done this before to calculate the exponents. We just want to see how things look when we have this extra relevant variable L, if you will. Okay, so after fixed large n steps, let me write the singular part of the free energy. I'll write in terms of, this is something I've written without the L before, so L to the minus 1. So there's n steps, so it's b to the minus nd. And the scaling dimensions pick up a factor of n, b, n, y. That should be t, h. Then you have that b there, so it's b to the n, L to the minus 1. And again, we know what b raised to the power n is. We fixed that. And that fixed number was something called k or kappa. So b to the n. So I'll just, without writing too many more steps, that gives me this is the T. This is something I'd written before. This is YH over YT, K, UH, and I've b to the n here, so let me also put in this expression. One over YT, and then it's just L to the minus 1. So then my free energy, again, absorb this fixed KT into the definition of T naught, all these tricks. This just gives me a T, a reduced temperature. So T over T naught, D over YT. The exact form of the free energy density, you'll often see written as a scaling function phi. Just means forget all the constants and stuff that you're not worrying too much about. This thing's fixed. This is proportional to H, and this is proportional to 1 over T here. So YH over YT. This is also proportional to the reduced temperature. So this is 1 over the reduced temperature, 1 over Y. So that's the same as T to the minus nu from this relationship. Right? And then L to the minus 1. So this is actually really nice. This is the free energy. Depends on, okay, so the reduced temperature dependence occurs here. I have a field. Oh yeah, when I do this, I'm going to set that field equal to 0, remember? For the susceptibility. So let's just take the second derivative, set the field equal to 0. You can do the same for the for the specific heat or for the magnetization or whatever you want. Whatever you want to collapse in your finite size system. But let's just do the susceptibility. So second derivative of the free energy. So the susceptibility is a function of temperature and system size. So this will go like T to the minus, that's the definition of gamma. We already related gamma to the scaling dimensions Y. So let's just write it as gamma. I have some function. Oh, it's some different function. I don't know. Tilde, whatever. These functions don't matter. Doesn't matter what they are. H is set to 0. So the only thing I have left in this function is this. And that's it. That's a finite size scaling form. So it means that your susceptibility has its usual divergence as you go to the critical point. But there's also a universal function which you don't care what the actual function is. But its dependence is on, just this relevant variable and how it's scaled. And so just to note, that thing, that's the correlation length. Right? So this is just like the correlation length over L. The correlation length is some physical length. And your finite size system that you're studying may or may not be, comparable to that correlation length as you approach a critical point. And, generally you'll have, if you're far enough away from the critical point, you can make your system big enough that your correlation length falls within the system. So you can imagine L, and then you have a correlation length. So in the case where this length is much smaller than L, then your physical observable will look like it's calculated properly in the thermodynamic limit. But you can also imagine that if you get close enough to criticality, your fixed maximum system size, say, your correlation length is nowhere near fitting inside that box. So physically, the correlation length will just approach L because it's constrained in your physical system, or in your simulated system, say. So then t to the minus nu will just go to L, and L will behave like your reduced temperature if it's raised to that exponent. So all it's saying is, if your universe is only the size of L, and you're close enough to criticality, then at some point the correlation length becomes your entire system, your entire universe. So you're not, in some sense, you're not containing the correlation length. You're not looking, if you will, correctly at the thermodynamic limit, but it doesn't matter because you can use the scaling function to look at the important physical properties. So therefore, for the susceptibility, let's say, I can replace that with just my system size. So it's gamma. It's gamma over nu. Then I have some others, my scaling function. I don't know, it's t, I'll just write phi. It keeps changing, but it's t to the L1 over nu still. So I can write it like that. And that scaling function is something that you can essentially plot for different system sizes for a range of values around your critical point, and use that to extract, the reduced temperature, the critical exponents, whatever you want. So what it means is, for any finite size system where your divergence is cut off by the fact that you can't access the thermodynamic limit, you'll see a function that scales like that. So that function phi it's analytic, but unlike the divergences that come from the coefficient, or like the divergences, it's still universal. So all you have to do is plot the susceptibility. So if you plotted the susceptibility as a function of temperature, which you can imagine getting out of your simulation, you would see a curve that because L is finite for a fixed L, I don't know, looks something like this. But if you vary L, the height of that peak, for example, near criticality, will scale as L to the gamma over nu. And the distance, well, I drew the peak right at TC, but in principle, the distance between the peak height and TC, or any feature on that curve, will scale like the argument of that function. Well, okay, so it'll scale as L to the 1 over nu, minus 1 over nu. So the argument of that, in order to get collapse, you put the argument of that function in there. So that's how it scales. It changes with system size. A feature on this curve will move closer or farther away according to that scaling. And say the peak height or any other vertical feature that you could track will scale as L to the Oh, what did I write? That's supposed to be a nu, right? Gamma over nu. And so if you replot the susceptibility, instead of the temperature, use the reduced temperature L to the 1 over nu. So the nice thing about doing finite size scaling like this is it takes into account a range of data that you might get from numerics, say, near your critical point. So what you're looking for is, what of it, chi to the L, nu over gamma, T, L 1 over nu. And you'll get different curves for different finite sizes. So for some L, you'll get, that's basically your function. And for another L prime, you'll get something that looks like that. And these can be very different L's. And so actually, the bigger your system size is and so on, the better your collapse will be, L double prime. So what you do is you adjust your free parameters. Say you don't know any of these exponents, nu, gamma, and you might not even know the critical temperature. By looking for collapses that are essentially perfect, near the peaks of these curves, what happens is they'll deviate away. So at some point, all this argument about criticality breaks down and your correlation length is too small. So you'll see deviations out here. But if you adjust all these parameters so you get perfect collapse near the peak, then that'll give you the critical temperature and the exponents. So you can still access criticality on finite size data if you know how to drive these scaling functions. That's the point. And in practice, you usually know something about your system. So for example, you might know from the symmetry, the Hamiltonian, and the dimension and everything, you might know the universality class. Then you just look on Wikipedia, you get the best values for the critical exponents. And so this is fully known. Everything's known except for the reduced temperature, and that'll give you the position of the critical point.
Is it also true that if you're doing numerics and you see a data collapse, does that mean that you're actually seeing the thermodynamic limiting behavior?
Well, in this sense,
right.
You're seeing a function that's universal, derived in the thermodynamic. The scaling arguments are thermodynamic, but you just treated this. This is what's non-thermodynamic about it, is you put in this relevant variable. So you could think of that L as like perturbing you away from the thermodynamic limit. It's like a relevant variable that pushes you away from the thermodynamic limit. But knowing how to handle it gives you access to, the thermodynamic values of all of these critical exponents. Of course, there's subleading corrections, so you can't just do this on two very small systems and expect to get highly accurate results. You basically need to push this calculation to very large L, say. And so this is what you're going to do on your computational assignment. You're going to calculate critical exponents using finite size scaling collapse of Monte Carlo data for the Ising model. So those exponents that you'll someday calculate, someday soon, they're known. They're basically known numerically. They're known from series expansion probably most accurately, or maybe Monte Carlo simulations. But one of the points of this class is we're also trying to calculate those critical exponents analytically. And so far, all we've succeeded in doing is calculate them in the mean field theory. So we did the Landau theory, then we showed that the Landau theory, if you start adding fluctuations to try to get like a perturbative expansion to improve those critical exponents, the whole framework breaks down. So we still haven't done anything about that. We've got some general like a general framework for the renormalization group. We've calculated exponents in one dimension, but then what happens in real space renormalization is, you know, in 2D and higher, it doesn't work. What the Hamiltonian couplings become non-self-similar. So every time you do an RG step, the couplings start proliferating. So you might start with a nearest neighbor Ising model in 2 dimensions, and then you do an RG step, and all of a sudden you get a third neighbor coupling. Then you do another RG step, you get a fourth neighbor coupling. So it's actually really impractical to do any sort of real space RG calculations to extract these exponents. So what we're going to do is calculate these exponents in momentum space. So we're going to forget the real space picture, although we've got a whole bunch of intuition, especially everything I wrote on that board at the start of class. You know, all the relationships between the variables and the scaling, the rescaling parameter B. Now what we're going to do is translate all that into momentum space. So any questions on all this scaling theory before I go on?
What is the dimension of decentralization? What? Yeah.
It's just because any linear length scales like this. That's L prime. That's all. It's like if you have a length scale, and you know you have some sort of ruler, and you take that and describe it with 2 rulers. One has been rescaled with a factor B. Then that length just goes down by, you know, so L prime goes down by B. Oh shit, L.
So it's like to cancel the units. B is length.
B's a factor. B's a rescale factor. So it's like if you have a lattice, and you redefine the lattice instead of, you know, A, you make A prime is B times A. So this is your new A prime. So that length scale, which is the same length, is just described by a different ruler, which makes it smaller. You made your inches bigger, so you made that length smaller in terms of those new inches. And so that's why it's just it's just 1 here. That's the basis of the whole thing, is the fact that you're doing that. Like this is basically the assumption under the scaling hypothesis. You've redefined the ruler. Other questions? We're just going to use that willy-nilly now. So momentum space, RG, it's called Wilsonian, presumably after Ken Wilson. And the idea behind Wilsonian RG is we're going to start with like the field theory with the action. You know, instead of the sort of microscopic lattice in real space, we're going to look at the Hubbard-Stratonovich transformed system. So then everything's described in terms of this action S. And we're going to eliminate degrees of freedom, just like we do here when we redefine that ruler. You know, we're going to eliminate all these small wavelength degrees of freedom, and we're going to do it in a momentum language. And that'll leave what's relevant for critical phenomenon, keeping in mind that you can have anomalies like the anomalous dimension. But phi's my fields. I think we've derived this. R is related to my mass in some language. If you don't know what that means, just forget I said it. R is related to small t, the reduced temperature. That's what changes sign. Remember? So this is like your Landau free energy, basically. It's, you know, phi 4 is a term that keeps stability when R changes sign. So like the parabola, when that part goes upside down, that signals the fact that you go through the critical point. And the phi 4 piece keeps this concave up. And the phi 4 piece comes from the Ising interactions. So the Gaussian part, which you can do a Gaussian integral to solve, is the non-interacting theory. And the phi 4 part and higher terms, phi 6, phi 8, is what comes from interactions. And that's what you can't do the Gaussian integration. And the fact that you can't do that integration of this action is basically what's difficult about interacting problems. You can't do perturbation theory. We saw how that broke down when you tried to include these higher order terms. So we still don't have a good theory for interacting, fixed points, if you will. And so that's what we're developing here. So we're going to perform the RG on this using the intuition we learned in the scaling hypothesis. So what is that? We're thinning out degrees of freedom. So we're thinking of short distances, short wavelengths now, because we're going to Fourier transform things. So thin out the short distant degrees of freedom in some way from this functional. Leaving what's important for critical phenomena. And we're going to do that by Fourier transforming the fields. So remember all your momentum space nonsense. So in real space, remember we know the scaling dimension of this actually. I'm going to write my momenta as K. Is that a mistake? Probably used Q before. I'm using K now. So the Fourier transform to real space has this, I guess, angular piece, if you want, or whatever in the Jacobian. And then I have a momentum space field. Just keep track of this sign here. And this integral is actually, over the radius of the spherical Brouin zone. Might not exactly be spherical, but we're constraining it to be somehow, so this is momentum space. In 2D, let me just, I have y, x and y. Then this is the radius of like a spherical shell or spherical zone. So pi by a minus pi by a, that's the limits here. So I can imagine some shell. Like that. And so there's some sort of cutoff. I mean, that integral is complicated. I mean, if you wanted this full zone, you would need some sort of summation. In the continuum, you want to have the spherical polar in momentum space. So you need to have some sort of high momentum cutoff, if you will. And that's what is that, lambda? It's how you regulate your theory to make sure that your integrals work. So it's not really well defined. You have some sort of UV divergence in principle. So one of the points with this type of momentum space calculation is you have to justify why that doesn't matter. So we're just going to write things in terms of that cutoff for now and discuss it as we go along. So it's all well and fine to write an integral like that for the fields. And we could go ahead and Fourier transform the action. But we already know that it's not going to be Gaussian if you have phi 4 in there. And so we're not going to be able to fully solve this problem just by regulating Gaussian integrals. So the RG procedure is our systematic way of basically handling this. So think back to real space. But keep that momentum picture in mind. So thin degrees of freedom. We had something like n prime b to the minus dn. Is that right? Sounds right. So we want to do the analogy of that somehow in the momentum language. And then we're going to rescale lengths. And again, the point is that you have a new ruler that you've changed the concept of a length with. And then at some point you rescale the length so that, if your b equals 2, you've gone from 1 inches to 2 inches. Then 2 inches becomes your new 1 inch. That's what rescaling means, right? And then you start the whole procedure again. So this is done by taking a thin shell around that yellow sphere and tracing out degrees of freedom there. And let's see, it'll be defined by B. So that's equivalent to increasing the lattice spacing. This is like A prime going to BA, like I was talking about over here. So in momentum space, that big lambda over B defines the inner shell. And then what we're doing is rescaling. Okay, so number 1, trace over all fields. Number 2, rescale lengths. And now we need momentum, the momentum version. So say BK. Yeah, since when I rescale X, it's inversely related, so my momentum's just linearly related. And then we have to also rescale the fields. And we kind of know how to do that already. But in this case, we have to rescale momentum fields. So let me just write it like this. And we'll figure out what this is like the scaling dimension. I could write it as b to the x. But some people write it as this z. Okay. We'll derive this next time. It's simple. You can do it. You just take the scaling dimension for the real space field and look at the Fourier transform. Okay, so I have an inner shell. Let me draw it again down here. So my picture is I have lambda, but I also have lambda over b. The thinness of that shell defines how good your approximation is in some later step. Thin out the degrees of freedom. So we're tracing over that shell. It's called momentum shell, RG, because of this. And then I'm rescaling, K prime. So all the field and, phi prime equals z to the minus 1 phi scaling gives me a new definition of my UV cutoff. So this is like the momentum space analogy to the entire RG procedure is defined in real space. And again, I think the important thing is you're increasing lattice spacing, which redefines or rescales your lengths. And from this, basically, everything that you derive here follows. Okay, so let's start with this action and massage it in a form that is going to be useful for this type of, momentum shell approach. What we have to do is take, a trace. So remember last time we traced over, okay, so in one dimension you trace over like even sites on the assignment. So we have to have the equivalent of that trace over that thin shell in momentum space. So we want to separate our momentum degrees of freedom into momenta that occur within this white sphere and also within this shell. So you need those two different, length scales, if you will, in momentum space. So let's look at that. B. If it's 1, you're not doing anything. But from this, we'll separate out those two momenta regimes. And I'll just call them fast and slow because of no reason, because of a velocity, say. You can call them big momentum and small momentum. Okay, I'll define what these are. So, for example, my real space field can be defined in terms of what I'll call phi less than and phi greater than. So the first one's slow. Okay, so it's fields that are obtained by integrating within the inner shell. What we really want is the momentum space version of these. And here I go, okay, so that's the inner sphere, and then I look at the shell. Phi of k, UDI, k dot x, fast modes. Again, I'm just distinguishing two regions, basically. And all we want to do is rewrite the functional in terms of these, your S, your action, if you will. so that we can integrate out the shell, and that's like our trace. That's the same as the trace that you're doing in real space. Okay, so I know what the functional is. Generally, there's going to be 3 terms in it. Just from a calculational perspective, there's going to be Gaussian terms. There's a slow and a fast mode, or an inner shell and outer shell Gaussian term that we can actually do the integration. And then there's the interaction term that basically involves the 5-4 that we can't do. So I'll call those S naught and S interacting. And I'll label them in terms of their slow and fast modes. So that's the full action. We're going to have a piece that's slow and a piece that's fast. And then we're going to have a piece that gets all mixed together because of the 5-4 term. So it depends on both of those fields. And so that's where you're going to imagine kind of exact calculations breaking down, because we're not going to be able to do Gaussian integrals here. These separate out because everything's Gaussian. So let's just look at that Gaussian piece first. So just the quadratic part of that action. Sure. There's your mass, R over 2 phi squared. And you already calculated this in momentum space. I'd belabor the point that this gradient gives you, k squared terms, remember? So let me just have that integration over the whole Bron zone up to the idea that there's some cutoff. And remember, because of the delta function, one of our fields in Fourier space has k and one has minus k, right? There's a constraint on the momenta from the delta function, and then the gradient gives us k squared, and then that, that's why I use x here, because r is not the distance. Keep that in mind. This is some parameter that's like proportional to t, or sometimes it's called the mass. And people might write it as m. But it's some parameter, remember, that changes sign as you go through the critical point. It's not a length scale, it's not a distance. So don't get confused by that. This is annoying. I'm just going to write this as 2 pi to the d. Let's see. I'll just write it like this. Okay, so let's see how these look separated in the slow and fast modes. There's no surprise. I have the inner sphere and the outer shell. And I would just write this term in terms of these two different, fields. One's slow and one's fast. There's the outer shell. One's less than, one's greater than. All I'm doing is confusing you by being too careful. I could have just defined the momentum, slow and fast modes. So this, slow mode is just that's like your block spins. And this is like your spins within a block. So this is just phi k. And that's what you want to trace out, right? Right, so it's like spins. This is like block spins. And this is like spins within a block. So momentum space, there's no surprises with the Gaussian term. We can just write those, let's see, phi naught slow. And fast. Okay, so let's not belabor that too much. It's the phi 4 term that matters. So in the phi 4 term, I have to consider the Fourier transform of 4 of those fields. And that Fourier transform and all the delta functions that occur and so on, these are basically what's going to give you a perturbation theory and Feynman diagrams eventually. So in the Gaussian case, sort of everything's simple, but in the phi 4 case, there's definite constraints that you have to work within. So there's the interacting piece. You can separate it into slow and fast modes. But all it is that second piece, or the last piece up there, so it's u over 4. Use just some parameter in the Landau theory. It's always positive. No. I don't want a Fourier transform yet. This is just straight up writing the action. Phi 4. These are real space fields, right? So I need 4 Fourier transforms. So I need K1, K2, K3, K4. Oh man, so four fields. So I'll label them K1, K2, K3, K4. And I have Fourier transform, so I have 4 fields, or 4 momenta in the exponential. All of those things dot x. So I've just Fourier transformed this piece here. So believe it or not, this is going to be easier than doing a real space calculation. As always, we can eliminate this integral by using a definition of the delta function. And what we need here is something like this. I hope I got that normalization right. So it means that the sum of those 4 momenta from that delta function, they all sum to 0. So when you go back and you start doing Feynman diagrams, you'll see that those all form a node within which, the Feynman diagrams sort of originate. So if I use the fact that I'm going to separate the fields into slow and fast modes, and these things are only defined in their respective regimes given by that orange chalk, Then I put this sum of these 2 fields into each place where this occurs. I already did that implicitly in the Gaussian piece. It just canceled. It just turned into 2 integrals immediately. Those 2 integrals are out there. But in the interacting case, we have to be more careful. Then of my momentum integrals. And inside there, I have things like phi of K1, so the slow plus the fast. That's just the first field. Then I multiply this by the slow and the fast for K2. K3. I'm only writing these to demonstrate that you're going to get all this mixing between slow and fast modes if you multiply this out. So the integral is going to be hard to separate. Question?
Yeah, so a question. When you did the phi square term, wouldn't you have also these mixed terms? Because the integral would be sort of like just half of this, right?
The integrals are only defined in the respective shells themselves.
Oh, okay.
So here, so when you have to restrict the definition to be just in those shells. But when you do that, it doesn't help you because you get all sorts of higher order mixing.
Okay, then we can say 2 regions. Okay.
So you have to be careful about that. That's basically the point. It's just not as simple as splitting those integrals into 2 regimes like you did in the Gaussian case. I just got to be careful. I want to write that delta function because we're going to come back to this expression. So remember where it came from. So that's why I wrote it like this here. So the interacting piece we have to be very careful with. So now that we're gonna do is we're gonna write the partition function and do the trace of that shell in as much as we can. Okay, so we're gonna trace out the Gaussian piece is gonna be fine. We're gonna get something that's like log of z naught, which we add to the partition function. We're just gonna throw it away. And so then we're gonna have to ask, how does that trace affect the definition of rescaled variables? So the strategy is we want to rewrite the action, the thing I just wrote or erased, the full action in terms of rescaled parameters. That means rescaled fields, but it also means rescaling U and R. And then we want that action to be self-similar. Just like we want the Hamiltonian to be self-similar in real space, the couplings. Right? So what you find again is that in 1D, that self-similarity is obeyed. The couplings are always nearest neighbor. But in higher dimensions, what I tell you, because I don't want you to try, is that those couplings proliferate so they're not self-similar. So what we need now is we need to be able to take a trace over the fast modes and then argue that the action is self-similar after that trace. Okay? If so, then we redefine all the U's and R's and fields, and that'll give us our RG step. That's it. That's all there is to it. So that'll take us another, I don't know, month. No, just kidding. It takes a while, but we'll just keep our eye on the prize. And I mean, what's going to be the difficulty is this term here. We're going to have to use approximations and some sort of perturbation. And that perturbation theory is called the epsilon expansion. Okay, questions? It's today Wednesday. See you guys Friday.